Hi there. We are ready for section 7.5 exponential functions. We have been talking about exponents. We solved exponential equations in section 7.3b. By the way, there is no 7.4, so don't be thinking you missed it. So now we're going to actually look at exponential functions, and we're going to graph them in this section, and we're going to talk about exponential growth and decay. So first things first, let's talk about the exponential function, and then we'll do a couple examples. So again, a function, just like an exponential equation, is an equation where the variable is the exponent. So, like we did in the last section, y equals 5 to the third power. We've got an x and a y because it's a function and we can graph it. The form is y equals a times b to the x. Notice in that form the x power is only on the b. It's not on the a. So you might have something, well, I'll do a couple examples, 2 bullets down. So it is a times a number b to the x power. A cannot be 0, because if it were 0, we'd just have y equals 0. B has to be positive, and b is not allowed to be equal to 1. And some people might think, well, then b must be greater than 1, right? But if it's positive but not equal to 1, excuse me, it could be like 1/2 or a third or a tenth or 15. So b has to be positive and not equal to 1. So here's some examples of what it would look like. You could have a y equals 2 times 3 to the x. Again, notice how the x is just on the 3, it's not on the 2. If you think order of operations, when we go to do the math, we're going to do 3 to whatever power we pick for x, and then multiply that by 2. Because remember, PEMDAS, we do exponents before we multiply. Second example, y equals 4 to the x power. Well, there isn't an a value, there's just 4 to the x. So it'll be like there's a 1 out in front if we wanted to look more like that green example. And my third example is y equals 1/2 to the x. Again, b is positive. It's not equal to 1. It could be a fraction. And those numbers, those values of b, do tell you some things. So if your b value is greater than 1, it's exponential growth, and we'll look at the graph so you can see it. Well, if b is always the number that's being raised to a power, in this example, I would say that b equals 3. So we've got exponential growth. In this second example, y equals 4 to the x. The b that's being raised to the power of x is 4, so that's exponential growth. If b is between 0 and 1, remember, it has to be positive, but it doesn't have to be, it can be a fraction. If b is between 0 and 1, so a fraction, it is exponential decay. So in this example, y equals 1/2 to the x. My b value is 1/2. So that means it's exponential decay. And you'll see on the graphs what those look like. And the last thing that I have to say leads us right into making graphs. Make a table of values to graph, or a values table. We're going to pick values for x. We're going to talk about domain and range. Values of x, remember, are always your domain. We get to pick anything we want to put in for that x value. Positives, negatives, zeros, whatever we want. So our domain will be all reals because we can pick any real number. The range, the y values, we'll talk about. And sometimes it's easier to see the range on the graph than it is to look at the table itself. All right, so I want to do all 3 of these examples because they all show something different, and that way you've got something in your notes. So let's graph these exponential functions. My first function is y equals 4 to the x power. It says to find the y-intercept. We know where to look for that. Let's do the graph and then look. State the domain and range and decide if it's exponential growth or decay. So make a table. Let's pick some values of x. Let's just pick some random ones. Let's do -2 to +2, just so we have a starting point. And I am going to include 0 in there. So when I put, you might want to get your calculator out. If I do y equals 4 to the -2 power, this is a good practice for those negative exponents, right? Y equals 1 over 4 squared or 1 over 16? I don't even know what that comes out to as a decimal, to be honest with you. Feel free to turn it into a decimal. I just know it's teeny. If I put a negative 1 in there, I've got y equals 4 to the negative 1 power, or y equals 1 over 4 to the first, 1/4 or 0.25 if you like decimals better. If I put a 0 in there, my favorite problem, y equals 4 to the 0, everybody knows what that answer is, right? Anything to the 0 power. If I put a 1 in there, y equals 4 to the first power, well, that's just 4. And last but not least, if I put a 2 in there, y equals 4 squared. Well, 4 squared is 16. I've got myself 5 ordered pairs. Let's plot these guys. So negative 2, 1/16. So it's super close to the x-axis. I'm not going to be getting out a ruler, but I know it's super close. Negative 1, I should really move that even closer, like almost on top. There we go. Negative 1 and 1/4. A little bit higher, but really, we don't, 0, 1. That's an easy one. 1, 4. And 2/16 shoots right off the graph. It's going to be somewhere up there. So let's connect these. Is this linear? Does it look like a straight line? Give it a nice curve. We are not graphing a linear function right now. We're graphing one with a curve. It will not cross. Go back and erase. It will not cross the x-axis. If we put in negative 100 and did the math, we would have y equals 1 over 4 to the 100th power. That would be some kind of teeny tiny, ridiculously, exponentially tiny number. Your calculator probably even say something to the negative 10 power or something like that. Super teeny, but never gets to 0 and never crosses 0. So two questions. Domain and range. Would you agree that we picked negative 2 to positive 2 for our domain, but we really could have picked any number we wanted? Negative 100, positive 100. So domain is all real, so we get to pick. Remember that was the all real abbreviation? The range is the y value. So look at the graph. Look at it up and down in the y-axis. This is my y-axis, right? What's the lowest possible value of y that we've got on there? It gets super close to 0 and goes up into the positive 16 and above, but it never hits 0. So I'm going to say that my range is y is greater than 0. It's not greater than or equal to. All of my y values up and down on my graph are greater than 0. I think the graph's the easiest place to look and find your range. But if you looked at your table, you would see that all of your values are positive. There are no negatives, so you'd know that y has to be greater than 0. And last but not least, it asks for exponential growth or decay. Well, first of all, if I look back at my equation and I know that y equals ab to the x, my b value is 4. If b is greater than 1, I know it's exponential growth. I also look at my graph. If you read it like a book from left to right, it's going up. So I know it's growth. Either way works. When we get into the third graph, it might look a little bit crazy. So I wanted to make sure we looked at the equation too. Example 2, we've got y equals 3 times 3/4 to the x power. So all the same things. Oh, I forgot to find the y-intercept. What's the y-intercept on this graph? Where does my graph touch the y-axis? That's going to be at 1, right? You can look at the graph and see where it crosses the y-axis, or look at your table. When your x value is 0, that is your y-intercept. When we're graphing lines, we said, oh, in order to find the y-intercept, you make x 0. So all the same questions for example 2. So let's do the same thing. Let's do negative 2 to positive 2, just to get some idea. I just like to be able to see what's the shape of the graph. Usually I'll use 3 points, but just so that we know what it looks like. So domain, does everybody already know what the domain? We picked -2 to +2, but you could pick anything you possibly wanted. So let's do some math on the side here. So y equals 3 times 3/4 to the -2 power. You might need to get your calculator. I'm going to do this the old-fashioned way. I know that that's 3 times 4/3 to the +2 power, which means I'm going to have 4/3 squared times 3. Gosh, I don't even know what that is. Let me do a little quick math here while you guys are doing your same calculations. I end up with 16/3, which is like 5 1/3. That's not a fraction. Let's get this. 5 1/3, 5.3 repeating, whichever you prefer. Plug in a -1. Y equals 3 times 3/4 to the -1. Well, I know that's going to be 3 times 4/3 to the +1, so I'm going to get a 4 for that answer. 0. The answer won't be 1 because, remember, we've got y equals 3 times 3/4 to the 0 power. Well, what's 3/4 to the 0 power? Big old 1, right? But we still have to multiply it by that 3 out in front. So 0, 3 will be my ordered pair. Let me make this work a little smaller. So now I want to plug in a 1. So I'm going to do y equals 3 times 3/4 to the first power. You may go to your calculators to do this. That's fine. But I want you to see what I'm actually plugging in. When I do that math, I believe that's going to be 9/4 or 2.25. 2 1/4. I keep switching between fractions and decimals. As long as you get these points on your graph where they make sense, kind of do whichever ones you like better. And last but not least, y equals 3 times 3/4 squared. When I do that math, I end up with 9/16 times 3. This is going to get me a decimal, like 1.26, something irrational, I think. I could put in 100 if I wanted, and I would get super teeny tiny 0 point something. So let's get these points on the graph. So -2 and 5 1/3. 1, 2, 3, 4, 5, and a little bit more. -1, 4, 0, 3, 1 and 2 1/4, and 2 and 1.26. And if we did others, they would end up getting closer and closer and closer to that x-axis. Do you see how we're going to have a curve? We could put a +3 in there. We could put a -3 in there. We get a larger number. But your graph should look something like that. Note to self. I'm pretty sure, I'm 96.3% sure that most of our graphs, all of our graphs, that graph is going to get closer and closer to the x-axis, but never actually hit it or cross it. But make a little note on that because when we're doing domain and range, that will help us out. So first of all, y-intercept. Where's our graph touching the y-axis? How about domain? Everybody knows, right? This is going to be very repetitive for domain. We can pick anything we want. There are no restrictions. If there were restrictions, we would have talked about them. To find the range, we're going to look at our y values. I just gave you a little hint. The lowest possible y value gets closer and closer to that x-axis. It never actually touches it, but our y values are all greater than 0. And last but not least, is this exponential growth or decay? If you read it from left to right, what does it look like? To me, it looks like decay. If we want to make sure and know that we're absolutely right, you look at your b value. B in this equation is 3/4, which is between 0 and 1. So we know that that is exponential decay. So let's do one more graph just to test it out. Y equals -2 times 2 to the x power. All the same questions, so let's just put our values in here. And let's just do our math on the side. So y equals -2 times 2 to the -2. Whew, it's a nice problem, right? When I put that in there, I've got -2 times 1 over 2 squared, or negative 2 times 1/4, which is going to be a negative 1/2. Check on your calculator if you doubt me. When I put in a negative 1, y equals negative 2 times 2 to the negative 1 power, so that's negative 2 times 1/2. I've got a negative 1 for that one. Let's put in a 0. Y equals negative 2 times 2 to the 0 power. Well, we know 2 to the 0 power, right, is 1. So negative 2 times 1 is negative 2. Let's put in a 1. Negative 2 times 2 to the first power. So negative 2 times 2 is negative 4. And last one, put a 2 in for that exponent. So negative 2 times 2 squared. Well, 2 squared is 4 times negative 2 is negative 8. So let's get our ordered pairs on here and we'll finish this guy up. So negative 2, negative 1/2. This is interesting. It's going below the x-axis. Negative 1, negative 1. 0, negative 2. Hopefully you just caught the y-intercept. 1, negative 4. And 2, negative 8. Does everybody see the curve in this? Do you see that even though it feels kind of upside down, it's getting closer to the x-axis, but I believe, just like the others, it's never actually going to touch it or cross it. Try to make a nice curve. Sometimes they get a little sketchy looking. So let's talk first about the y-intercept. What's the y-intercept? Everybody agree with the negative 2, right? Domain. Did we get to pick anything we want? Could you pick numbers other than mine? Are there restrictions for what you can or cannot pick? No. So all real numbers. Range. This one's interesting because if you look at the y values, would you agree that all of our y values are less than 0? So my range for this one is all y values that are less than 0. Not equal to, though. Remember, I told you it's not going to touch or cross, so it's got to be less than 0. And last but not least, exponential growth or decay. This one's interesting. Is your first thought that it's decay because the graph is going down? So this is where when you've got something that you're not 100% sure, go back to your y equals ab to the x and look at your b value. Your b value, remember, is always the one being raised to the power. B equals 2. Well, if your b value is greater than 0, it's exponential growth. The reason that it looks crazy like that is because of that negative 2 for the other. It got flipped over the x-axis. So it actually is exponential growth just on the opposite side of that. Let's see if I can flip this. So really, we've got that, but it got flipped over because of the negative 2 for that a value. So if we look at it that way, it would be growth, only we flipped it over. So look at the b value. That's the best way to make sure you know that it's exponential growth or decay. All right, so last but not least, let's identify some exponential behavior. First of all, exponential functions have a common ratio. We use r. Remember when we were doing arithmetic sequences, we had a common difference that we called d. Well, difference was what we added or subtracted. Ratios are what we multiply or divide. So make yourself a note if you need to. The y values must multiply or divide for the r, the common ratio. The x values just look for a steady increase or decrease, like the x's are always going up by 1 or by 10 or by 5 or something. So it's really the y values. So determine whether each set of data displays exponential behavior. In order to do that, we're going to have to identify the r. So for a number, letter A, would everybody agree that these are going up, x's are going up by 10s? So just to verify, we're good. The x's really don't make a difference unless they're not increasing at a steady rate. The y's, however, are what we care about. What do you do to get from 80 to 40? How about from 40 to 20? Does this hold true? How about from 20 to 10? How about from 10 to 5? How about from 5 to 2.5? What would be your next value after 2.5? I'm saying a 1.25 because what did every y value, what happened? You took half of it or divide it by 2. So dividing by 2 is the same as multiplying by a half. So we took r is 1/2 because we always took half of that value. So for the second one, are our x values increasing at a steady rate? Everybody's saying yes, right? These are always increasing. I didn't purposely pick all values that had tens. It just happened that way. So we're good with the x's. Now let's check the y's. How do you get from 15 to 21? How do you get from 21? I should have put yes up here, by the way. 21 to 27? 27 to 33? 33 to 39? Do we have multiplying or dividing to get from one y value to the next? It looks to me like these are all adding 6. Well, we said the y values have to multiply or divide. So this is not exponential. If we graph this, this would be a nice straight line. We could figure out the slope, we could figure out the equation, all that kind of stuff. So this is not exponential because the y values subtract, or sorry, add, wrong direction. The y values add, they don't multiply or divide. So let's talk about this last one. This one's a good one. First of all, x values, pretty good, right? Like I said, I didn't purposely pick where they always added. So the x are good. It's just, make sure. How do you get from 10 to 25? We could add 15, but does that work for our next? How do you get from 25 to 62.5? I went to my calculator and I did 62.5 divided by 2.5. And then I checked 156.25 divided by that value to see if I got what I needed. So when I did the math, it looks to me that I multiply by 2.5. I'll do it times 2.5 times 2.5. So this is an exponential because my ratio, common ratio, is 2.5. I multiplied every one by 2.5 to get to the next y value. All right. So, lesson summary. In your own words, describe how to determine if a function represents exponential growth or exponential decay. What do you look for? How do you do that? If I say, here's a graph or here's an equation, how do you know if it's exponential growth or exponential decay? And your practice problem, there's a little table right there. Does that little table, just like those 3 that we just did, does that represent exponential behavior? So does it pass our test? So look at your x and your y values. If it is exponential, what's the common ratio? Don't be fooled. This could be tricky. Have a good evening. We'll see you guys next time. Whoops.